Good afternoon. Welcome to Wrangling Complexity Breakout Session number 2. I'm Nan Mattai. I'm Senior Vice President of Engineering and Information Technology at Rockwell Collins, and I will be serving as your moderator for this session. I would like to go ahead and introduce the panelists. Starting to my immediate left is John Clark. He's the Director of Focused Technology Roadmaps at Lockheed Martin Skunk Works. In this position, he's responsible for maturing and transitioning technologies to address the needs for all of the aeronautic platforms. Next to him is Evan Fortunato. He's the co-owner of Apogee Research. Previously, he was a director at BAE Systems and a program manager at DARPA. Evan's research interest includes adaptive and resilient cyber-physical systems. Next to Evan is Kathleen Fisher. She's a professor in the computer science department at Tufts University. Previously, she was a principal member of the technical staff at AT&T Labs and a program manager at DARPA. Kathleen's research focuses on advancing the theory and practice of programming languages. Next to Kathleen is Richard Murray. He's a professor of control and dynamical systems at Caltech and an elected member of the National Academy of Engineering. Richard's research is in the application of feedback and control to network systems with applications in biology and autonomy. So why are we here this afternoon to talk about wrangling complexity? Well, as an engineering leader, I'm often asked the question, what keeps you up at night? And what are the biggest challenges facing product development? And at the top of my list is usually designing systems that work on time, on cost, in an environment of increasing systems complexity. So let's take the example of the F-35. Lockheed Martin refers to this as the digital jet for the modern battle space. So Rockwell Collins is very proud to have been responsible for the development of the helmet-mounted display that is an integral part of the F-35. All the information that a pilot needs to complete his or her mission is actually projected onto that visor. Information like airspeed, heading, targeting information. In addition, the pilot is able to see a 360-degree digital view of what's going on around the aircraft. If the pilot looks at his feet, instead of seeing the cockpit floor, he sees right through it at the terrain below it. But the development of this advanced system, very complex, was not very easy. It was very challenging, had setbacks, and sure enough, cost overruns. In fact, things got so bad, things were so at the peak of the issues, that in 2001, the Pentagon contracted with BAE Systems to design a backup system just in case we were not able to work out the kinks of the Gen 2 design. Fortunately, that's behind us today. We were just able to deliver the Gen 3 version, which has largely resolved many of those problems to Lockheed Martin. But what is the takeaway from that story? This is something we face every day in aerospace and defense. We are designing very complex systems, and keeping them on time and on schedule is a bigger and bigger challenge for us. So with that, I'd like to share with you, this subject has been written in white papers. It's the subject of a lot of research. And in the Society of Automotive Engineers, Dr. James Truchard, who is the co-founder of National Instruments, was actually talking about keeping pace with increasingly intelligent machines. And if you look at that red box, you'll see his comments. He said he used words like rapidly evolving complexity and the need to evolve the methods that organizations use to design and validate those embedded systems. And our panelists are going to be discussing more on those areas as we progress later in this breakout session. But the aerospace industry is not the only industry that's seeing this complexity. Just think of the automotive industry and what's been happening in that industry. Today, cars are no longer only a mode of transportation. We think of them and purchase them like tech devices. Think back to 1950 when a mechanical engineer was primarily responsible for the car's design and how that's changed over time. Most of the, many cars today are computer controlled. And actually, the low-end cars can have as many as 30 to 50 electronic controlled units, which are talking to each other over controller area networks, CAN buses. And the amazing thing is that a typical car has about 10 million lines of software code. The higher-end cars has as many as 100 million. To put that in perspective, the F-35 has 8 million lines of software code. 90% of its functions are managed in software. And the Boeing 787 Dreamliner has about 14 million lines of code. As we look at the trends today, we know that this trend will continue into the future. So to stay ahead and to be able to design those systems of tomorrow, I believe we have to do two basic things to survive. Develop safe, secure, and affordable systems for our customers. We have to reduce the complexity, and we have to improve the complexity that remains through novel design practices, new tools, and new technologies. And so with that, I'm going to turn it over to the panel to discuss what approaches and technologies they're working on, starting with John.
All right, thank you. So as we look at the DoD side of this equation, and specifically looking at the aeronautics element of our systems, there's a lot of complexity that's emerging associated with how these different systems interoperate with one another. If you look at how our systems have worked as a function of time, interoperability has really been an afterthought with a lot of the development of the systems, and the complexity has been isolated to an individual node or an individual platform. As we go forward, there's an emerging trend where the sensors talk to the sensors, where you have the individual platforms working with one another in much more complex ways. Historically, you've got systems that have worked off of Link 16, and there's a very finite set of interactions that can occur via Link 16, and the method in which those systems interact is really pretty constrained. And as we go forward, there's a lot of opportunities with the airborne systems to get much greater interaction within the systems, whether that's F-22s talking to B-2s that then talk to F-35s that then have connectivity to the entire terrestrial infrastructure of the intelligence community. There's a lot of interactions there that's going to drive complexity as we go forward. As you decompose the aircraft and you look at those individual systems, every one of those systems becomes another endpoint that produces and consumes information that really drives complexity inside of the systems, because that information, not only does it have to be understood and consumed, it has to be done in such a way that meets the safety and mission critical facets of the systems. With that, we see a lot of complexity that's going to emerge within our systems in terms of how we go about fighting in an A2AD environment. In one of the previous sessions, I actually talked a little bit about, or one of the questions centered on the bumper sticker on the chart, about information overload. The reality is that as these systems and devices become more connected, there's more and more information available for these systems to consume, which is then one more level of challenge for the system to be verified and validated to operate correctly with the data that's available, and then how does it understand what data it should use and what data it should not use based on the adversarial environment. So in that spirit of managing complexity, you look at our DoD environment. We have very different timelines where these systems have been developed. We have a B-52 that's been out there flying for more than 50 years and does a great job for what it can do, but the ability for it to interoperate with other systems and fight in a more digital battle space is rather limited. With these finite interfaces that have been established, there's not a lot of standardization for these systems to interoperate with a common language. Because of the different timelines with their development and the fact that we're putting out aircraft at a much lower rate than we have historically, you end up with a lot of unique interfaces within these systems. And so the interfaces of an F-22 are different than the interfaces of a B-2 that are different than an F-16. You can go down the line. There's other than a couple of basic standard implementations, everything is unique to those systems, and the ability for those systems to interoperate at very deep levels is limited. As you're trying to take advantage of information that could be exposed in the network and make decisions on that information, you find that you have to jump through a whole bunch of hoops to get that information, whether that's tunneling information from a terrestrial network that's now hopped 3 times. It becomes a big challenge to get that information. Within the last decade, there have been a number of emerging efforts to try to attempt and address this idea of getting a common language of sorts for these mission systems and different nodes to communicate with one another. I've highlighted a few of them here. The UCI effort focused on getting interoperability between different command and control components within a ground station to facilitate reuse of software within a system. That went a long way toward highlighting how you could take what would be otherwise custom-built interfaces to do the same thing and standardize them in a way that you could actually begin to get reusable software components. And that's the basic tenet of the Lego analogy depicted on the chart. You're establishing common interfaces that are well understood and defined such that you can start to interchange these parts. The Open Mission Systems effort with the Air Force has actually taken that a step further and looked at taking that same sort of standardization approach and applying it into an embedded environment. Applying it to that embedded environment brings with it another level of challenge associated with real-time communication, how you interact with the safety-critical nature of the system. And those things have all been addressed in a standard way as a part of that effort. In parallel, there's also been efforts with the Navy and the Army, specifically highlighting the Navy interoperability profiles. There's also the UCS effort as well as the FACE effort, all really aiming at that same idea of getting some standardized ways in which these systems interoperate with one another. As you start to provide or enable this interoperability, it then brings to the forefront some additional questions that challenge how you interact with them. So I've highlighted a few of them here. So who's authorized to control those, provide control to those systems? So if I can expose the interfaces to the radar on an F-22 for another system to control because they need some information from that radar, how is that authority going to be managed? Who is going to get to make the final decision? And how do we make sure that that doesn't compromise what the actual system is doing at that point in time? How do we trust that the data that has been received externally is actually from a trusted source and not an adversarial source injecting information into our system that could then prove problematic for our activities? And then really one of the biggest problems that we have with this is that as we continue to expose more and more of this data, can the network handle all of the data? And it's not just about the physical network. You have to think about the RF or optical networks of communicating internodal in an airborne environment. And with the technologies that exist today, there's really a limited capacity to move high amounts of data in a true network as opposed to a point-to-point fashion. So with these activities, the standardization has helped us get a long way, but it's not an end-all be-all. It doesn't solve every problem. The standardization does help break the problem into more tractable components for people to start to work toward and facilitate better systems engineering of the systems. However, as you begin to get these systems and you start to implement these standards, everything starts to get very rigid. So a couple of examples here. You have Link 16 and Standard 4586, widely proliferated standards and something that is used throughout the DoD. The issue with those standards, however, is that if you want to change to Link 16 or you want to change to Standard 4586, get in line and wait many, many years before that change manifests. So what this precipitates is that the technological part of the industry or the new emerging programs start to look for ways in which to solve this problem, which drives uniqueness. You can't get all the information you want to exchange among Link 16 because it was designed 30 years ago with fixed format messages, and the type of content going across a TDMA network is pretty limited. If you look at where we're going in the future, there's going to be a much more diverse set of information that needs to go across that network, and it's not always going to be static or a fixed format structure. Similarly, if you look at the challenges associated with building consensus with these standards, once they're ratified and you're going through a process of getting changes to be made, it can take a significant amount of time, or you just end up in deadlock. And the challenge basically compounds itself because any change that you want to make begins to impact another system, which drives cost to their system, which they don't have the money to facilitate, which drives them to then be interoperable if the change gets made, or non-interoperable if the change gets made. So it becomes a very tense situation where you're trying to move the system forward. So to make these things work, it's my assertion that you need to find the balance with the standardization. Standardization helps break down a lot of the basic barriers so that we're all speaking the same language. However, there's still going to be some unique dialects to that language that have to be addressed and may be different among different systems. So, can we use inline adaptation to facilitate that? How do we recognize that bad information is in the system? So specifically, the DARPA SOCITE program is looking to address a number of these challenges such that you don't become beholden to the standard. You can use the standard as an enabler to be a springboard, but not become the end-all be-all for your system and then lock you in. So with that, I'm going to hand it to Evan Fortunato, who will discuss that facet of the discussion.
Thanks, John. Good afternoon, everyone. So I'm going to be talking to you about creating interoperability without having a common interface. What an odd concept. Let's go ahead and dive right on in. The goal here, the underlying problem we're trying to solve, is composing systems that keep up with the time, that don't get rigidly locked, as John just described. Now, DoD is not very good at this, as we all know. In fact, they long assume that to get their superior fighting force, they need a predictable, homogeneous, fixed configuration system, that they know what it will do for 30 years out. But of course, designing for a 30-year-out requirement with today's technology is darn near impossible. So the result is that you get the best design possible with 20 to 30-year-old technology by the time these systems are being used. That doesn't seem like a great choice. The government knows this, and so they move towards different solutions, like the open architecture solutions that John has just described. And they've made good progress there, but they do have some issues. First, there's a lot of work to reach global consensus. And once you've reached it, you're stuck with it because no one wants to renegotiate. Exactly that tension that John describes. But the problem is, even if you reach global consensus, it's not really global. You get the Air Force on board. What about the Navy and the Army? You get DoD on board. What about the intel community? You get all the US government on board. What about NATO? There's always yet another global standard right around the corner that you're not interoperable with. So they're really just larger local standards. The bigger issue, though, is that when you try and get a global standard that tries to be everything to everyone, it's not what you need for your application. We've all experienced that frustration of living in a bureaucratic system designed for someone else's needs that you're forced to use. Why suffer through that? Now, going further, even if you do all this, the result is that you get heterogeneous components, those Lego blocks, but in a completely homogeneous architecture, one that you can't change. And so as technology revolutions come, you're stuck with out-of-date architectures. So we try and anticipate the technology revolutions and build in adaptability to our architectures. But anticipating technology revolutions is a bit of a fool's errand. And so the result is we just get it wrong and make more complex systems that are harder to use, compounding the issue further. This seems like a bad road to be going down. What if we took a step back and asked, could we achieve our goal, creating interoperability, without going through the path of simplifying the complexity, creating a static common interface for all, but instead by embracing that complexity for a different solution. So to do this, we need to understand the underlying problem a little bit more, which is getting systems to understand one another. So I'm using a DoD example here to illustrate the point, but you can imagine commercial applications just as well. So imagine I've got two communities, Air Force and Navy. And systems in the Air Force, some can talk to each other, and some systems in the Navy can talk to each other, and some outgoing systems between the Air Force and the Navy can talk, like the Distributed Common Ground Station. Now you'd think with a name like Common Ground Station, they'd be common, but that's unfortunately not the case. So now I need some new interface. For instance, some Air Force UAV has data that I want to get down to the carrier group, the Navy carrier group. But of course, we can't anticipate all the interfaces. And even if we did anticipate them, we can't afford to build them all. So now we need to do this on demand. And we need it sort of now. So what are the options? They're not very good if that interface wasn't anticipated, which most of them aren't. We can do an acquisition, spend millions of dollars in many years, and get an interface probably after we need it, and probably that UAV isn't relevant anymore. It's a new UAV with yet a new interface. So we haven't really done anything at all except spend time and money. We could relay the information through all these other systems, send it down to the ground station, relay it through the DCGS, on through this loop. But that just seems like an absurd waste of very capable, expensive equipment just to play telephone chain. There must be a better way. And of course there is. And it's the well-known concept of abstraction and composition that is used in the software industry again and again. But in this case with a twist. Now many people have tried to abstract the interfaces, but the challenge is what part of the interface to abstract. You need to know that beforehand. And as the system evolves, you get it wrong. In this case, we're going to take a different approach. Instead of trying to abstract the interface, we're going to abstract the differences between interfaces. So for instance, if I've got a representation of the data for the Air Force UAV, and I've got a representation of the data for the Air Force ground station, the yellow link depicted on this slide represents the transformation, the differences between those two representations. It converts from one to the other. It's a completely local, pairwise discussion. I don't need any global consensus. I just need to negotiate between two. Now I can do this for all the other links, the green link, the blue link, and the purple link. And now I get a very amazing effect. If I take UAV data and I push it through a chain of the yellow link, and then the green transform, then the blue transform, then the purple transform, out pops Navy carrier group data. Well, I put in Air Force UAV data and I get out Navy carrier group data. They weren't common. They'd never negotiated an interface between them or a conversion between them. And to be perfectly honest, I, as the designer, have no idea what that interface is. But by representing each of these transforms abstractly, then recomposing them and concretizing them, I actually get the result I want. So I need a way of efficiently representing this information, and as is often the case, graphs are a very good way of compactly representing a combinatory explosion of options. So as with all graphs, you have nodes and links, and you could use a different representation if you like. We just like the graph. Now the nodes capture the interface and the properties of that interface, but they do it in a completely local way. So I define my time and my space, and I can use meters and miles or whatever I like. It doesn't really matter. And now I negotiate just a small number, pairwise, of these links, these transforms between my interface and someone else's. Now I don't need to do it to everyone in the community, just one or two. And then they do it to one or two, and they do it to one or two. And that creates these long linear chains, which I can then use to create on demand all the interfaces I could ever want, without needing to go through all the problems I described on the previous slide. So this actually allows quite a large number of things. It's sort of remarkable how much this allows. Let me walk through 4 of the most important ones. First, by capturing those differences and abstracting the changes, the transforms, not the interfaces themselves, I can chain them together to create interfaces on demand. And I can optimize those interfaces for just what is needed between me and my partner this time. I don't need to worry about what everyone else needs. It's utterly irrelevant to me right now. It's optimized for my need. Well, that's great. That's interoperability without a common interface. But much more is allowed. So the next thing you want to do is come back to the original claim of what the goal was, creating systems that keep up with the times, that evolve, that change, so we don't get trapped in this standards lock. This is allowed because as a new system comes online with a new representation, all you need to do is relate that system through one link to anyone else in the graph. And once you've related it to one in the graph, you can then leverage everyone else's interface abstractions to get to anyone else in the graph. So now I can evolve the architectures to new representations without anyone even knowing or caring. Well, if I can do it to add one, I can add communities as a block. So imagine I've got two communities, A and B, Air Force and Navy, research and operational, whatever you like. Each has developed their own set of standards, their own set of interfaces, and now I want to make them work together. This is the big nightmare that DoD can't face. The amount of work it would take to do all of those pairwise interactions is just unimaginable. It's n squared work. But in this case, all I need to do is take one node in Group A and one node in Group B and link them together. And now any subsystem in Group A can follow the graph to its bridge node, hop across the bridge link we've just added, and then follow the community B graph to any other node. And so I get full interoperability between the two communities for a very small amount of work, just adding in a couple of transforms for that type of message. Now, the last thing it does is, by putting in those properties, again, in the completely local representation, so I don't need any global ontology or global model, I can actually install security checks to make sure my systems are behaving the way they should be behaving, both for security and resiliency purposes. So this allows quite a few different things. They're very nice things. It's a different way to look at the problem. It's embracing that complexity rather than trying to avoid it by creating simple interfaces. But it does require some new tools. Now, I say new, they're not really new. They were used very often in other communities. First, you need design space exploration tools that let you automatically explore different synthesis. Pathways through the graph, for instance. What's the right approach for you? Second, we need to concretize these abstract concepts into optimized instantiations. Well, that sounds a lot like a domain-specific compiler. And finally, of course, we need estimation and control techniques to ensure that the property checks are being enforced so that we have some confidence that the system is going to behave the way we want. So this represents an example of how, instead of avoiding the complexity, we can embrace it to get very adaptive, resilient systems. With that, I'm going to turn it over to Kathleen, who will talk a little bit more about the computer science perspective on this and how it's been applied.
Thank you, Evan. Right, so I'm Kathleen Fisher, and you can think of me as an ambassador from the computer science world to the world of systems engineering. So computer science systems have a lot of intrinsic complexity it comes from a synthetic means, right? Computer scientists build the lines of code that they then have to manage. But even though it's synthetic, that doesn't mean it's trivial. The slide here shows a couple of data points from one software project that's of some interest to many people, which is the Linux kernel, the GitHub repository. So the top graph, the horizontal axis shows time, and the vertical axis shows the number of commits per year. So the bars on the right-hand side are showing that in the last couple of years, there have been more than 70,000 commits each year, which means every day there are more than 200 commits made by people who are working on this collaborative project distributed across the world with no sort of centralized management and no hierarchical reporting to chain to make that happen. The bottom graph shows the lines of code that these people are working on. Again, the horizontal axis is time, and the vertical axis is lines of code and scientific notation. So on the left-hand side, in 2005, it was 6 million lines of code, and in 2016, it's up to 20 million lines of code. So quite a lot of complexity. Like, no single person can keep 20 million lines of code in their head. So we need to have tools and techniques to manage this. And computer scientists use abstraction and composition as the main tools. This was a major area of research in the 70s and 80s. There were 5 or more Turing Awards given for this kind of work. So the Turing Award is essentially the Nobel Prize for computer science. So there's a lot of attention paid to this area. So what is the idea? Basically, instead of thinking about the whole thing that you have to do, you break it up into chunks. Each chunk does a manageable amount of work. So on the slide here, I'm showing a chunk allocated for the SCL4 microkernel. It's a small operating system that manages different processes, the resources that those processes need, and the communication that can happen between them in a very tightly described way. It has interfaces. The interface on the bottom describes what SCL4 assumes. In this case, it's a hardware interface, so what it assumes about the hardware it's running on. The top interface describes what services, what it provides to its clients. And the role of those interfaces is it documents what is expected and what is required of the environment that it's working in. And that means people working on that code are free to change anything in that box. They can work in isolation to make the SCL4 microkernel better or more efficient or whatever they like in a way that's isolated from the rest of the system. And so the rest of the system can be evolved separately. So that's the idea of abstraction allows you to build components in isolation. The idea of composition is what allows you to build large systems out of these individual pieces. So in the HACMS program, which I was one of the program managers for, we built software for 2 air vehicles. One is a quadcopter that you can buy from Amazon, and the other is Boeing's unmanned little bird. So one's a helicopter big enough to fly a pilot and to have a passenger, and the other is a hobbyist UAV. But they share the same fundamental architecture, which is shown on the slide. There's 2 computers. One is the mission computer that controls things like where the copter should go, what it should take pictures of, and things like that. The flight computer controls the flight control software, so things like stability, for example. The mission control computer is running SEL4, the same SEL4 that is running in many cell phones, and that DARPA has a SBIR program right now where 4 different companies are working to use the same SEL4 microkernel in very different applications. The same abstraction barriers are like the eCronos is a real-time operating system that HACMS researchers are using on the flight computer, but eCronos wasn't quite ready in time, and so they were able to pull that component out and instead put in the free RTOS, which is a different RTOS that happens to satisfy the same interface. So because the system was developed with the discipline of a compositional architecture using abstraction barriers, they were able to do that substitution relatively easily, swap in the 2 real-time operating systems. So that's the beautiful case where abstraction and composition work well, but of course there are properties that aren't easily captured in interfaces. These are kinds of things that provide emergent behavior. So the telecom industry really worries about the feature interaction problem where you enable different features and they clobber each other and produce behavior that nobody wants. Security, which is of course a very important property of the DoD, is another emergent property. It's not a property of any individual component, but rather how all the components interact together. And then resource utilization, how much time is required, how much memory is required. Often computer scientists solve these problems by over-allocating, so making sure that the system has so much memory or so much time that it easily satisfies these requirements. And when you have systems that are more tightly driven toward the boundaries of the resources, that's when you have to do lots more careful reasoning. So computer scientists work as hard as possible to put everything into the domain of interfaces and abstraction and composition, and only switch over to tools to reason about these kind of emergent behaviors when they're absolutely forced to. So there are a bunch of tools that can help with these kinds of emergent behaviors. The slide here shows 4 different categories of these tools. The categories range in terms of how much effort is required to apply them and what level of information or guarantee you get out as a result of using them. So one example is Rockwell Collins' AGREE tool for assume guarantee reasoning that they used in the HACMS program to prove that the air vehicles had desirable security properties. Things like only authenticated and well-formatted messages that reach the quadcopter would be executed by the quadcopter. So an adversary that wasn't authenticated wouldn't be able to make the quadcopter fly off into the sunset. Now that high-level property that the adversary can't make the quadcopter fly off into the sunset is not something that you can just chop up and prove that same property of all of the components of the system. It doesn't even make sense in terms of some of the smaller components. But you can take that high-level property and break it down into pieces that if those pieces for each of the components are put together, then you do get the property that you want of the overall system. And each of those component pieces, the way you write down the property of that component piece is it gets to assume certain things about the environment. And if those assumptions are correct, then it provides guarantees about the environment. And you prove each of those pieces in isolation, and when you put them all together, you establish that if all of the assumptions were validated, then all of the guarantees are able to hold. A different approach is model checking. Model checking, basically, you capture a model of the system and some property, and model checking uses sophisticated techniques to search that space of models to determine whether there are counterexamples, places where the model violates the desired property. Microsoft was very clever about 20 years ago, 15 years ago. They figured out how to apply that same technique to actual software, not just to high-level mathematical models of what the software was supposed to be doing. And they used this to be able to make their systems more robust. So they were having this problem of the blue screen of death, where you probably remember the blue screen of death, and you probably also haven't experienced it recently. The challenge for Microsoft was that that blue screen of death was not really their fault. It was coming from their third-party vendors who were providing device drivers, and it was bugs in the timing properties and the non-termination characteristics of those device drivers that was causing the blue screen of death. But you, the user, didn't know that. You just blame Microsoft because it was Microsoft that was showing you that blue screen of death. They developed properties and model checking technology that allowed them to apply, to analyze the device driver code supplied by third parties and reject those that didn't satisfy the properties. And now third-party device drivers are required to pass a set of properties before they're allowed to be installed, and which is why you don't see the blue screen of death anymore. Another kind of tool for managing these kinds of emergent property are things like static analysis. So static analysis is mathematical analysis of the code without actually running it. Facebook just developed the infer technology that they run every night over the entire code base. So this is millions and millions of lines of code. And they're looking for they basically prove that there are no null pointer errors and there are no resource leaks. So proving that no resource leaks, that's one of those kind of emergent system-wide behaviors that they're able to do overnight using this tool. And then the far extreme standard of tools are interactive theorem provers, where you can prove incredibly strong properties about your software with concomitantly high resource allocations to do that proof. Right, so SEL4 is about 10,000 lines of code, and in interactive theorem prover, researchers at NICTA proved that it was fully functionally correct, which is an amazing tour de force. Right, they proved that those 10,000 lines of code did exactly what they were supposed to do and didn't do anything else. Researchers in the HACMS program showed how they could leverage that level of understanding and knowledge of that particular artifact to be able to produce quadcopters and Boeing's unmanned little bird that has unprecedented levels of security. Part of the proof of the SEL4 correctness is that those processes that are running on top of the core, on top of SEL4, don't share any information in time or space except that which is explicitly allowed. So again, time and space, those are emergent properties. Right, so I was mentioning what the HACMS researchers were doing with these kinds of tools. They built software for the quadcopter and for Boeing's unmanned Middlebird. At 18 months, they were able to fly the quadcopter. It was about 75,000 lines of code developed using the techniques and the tools that I've been describing. The quadcopter had stability control, altitude hold, directional hold, denial of service detection, and about 80% of GPS waypoint detection. They proved system-wide properties using this assume guarantee reasoning framework that I talked about. And then they gave it to a red team. The red team had full access to all of the source code for the system for 6 weeks, and at the end of that time, they were not able to break in and take over control of the quadcopter, which they were able to do easily at the beginning of the program before the HACMS researchers had a chance to look at it. That was just at 18 months. At 36 months, which was just a few months ago, the HACMS researchers were able to conduct a flight test on the actual unmanned Little Bird. This was 18 months early. The test pilot who was in the unmanned Little Bird reported that he detected no differences between running on the formal verified version and the previous version, which is, of course, exactly what you want. You don't want your assured code to behave less responsively than the previous code. And then to test the security of the system, a red team was given root access in one of the partitions on the mission computer of the unmanned Little Bird, and they were not able to break out of that partition. They were not able to disrupt the smooth operation of the Little Bird at all. So, this kind of security, this really high level of assurance, is not something that all systems need to be developed to, but this is a proof of concept that these kinds of tools can allow us to build systems that are super secure. Thank you.
So my name is Richard Murray, and I'll talk a little bit about wrangling complexity from the point of view of control theory. So what is control theory? If you've taken a class in control theory in the last 20 or 30 years, you've probably seen a diagram that looks something like this. The idea in control theory is how do we interconnect sensing, computation, and actuation in a feedback loop and use that to provide performance for a system. And so there are a number of ways that we like to do this. We might like to make a system stable. We might like to make it high performance. But the basic idea is that we want to combine understanding of dynamics, uncertainty, feedback, and feed forward to get systems to do what we want them to do. And the basic idea in a feedback system is that if we can sense the output and we know what we'd like that output to be, then we can do a computation and say, okay, well, if the output's not what it's supposed to be right now, then how do I modify things? So if this is an autonomous vehicle and it's driving along the road and you'd like to be going at some speed, then you look at the speed that you're actually going, the speed that you'd like to be going. You reason about, how much should I push the accelerator in order to speed up in a smooth way, and you apply that action. And then, as the car starts to accelerate, you do it again. And you do this over and over and over. And because it's in a feedback loop, you have to be careful about how you reason about this, because causal reasoning doesn't always work, right? Because you make some change, and that changes something, which comes back and changes the very thing that you sort of started to change, right? Because it reacts to you. And so control theory is the discipline where we think about these interconnected systems and how to reason about them. So control theory is a field that's 50 or 60 years old, and so these are the early ideas. And so the systems that you see on the left, so the steam governor and thermostats and aircraft are the types of systems that control theory was designed to do. But as control theory has emerged, it started to look at other classes of systems. And so I think a modern view of control theory would say that what control theory is it's a collection of tools and techniques for analyzing, designing, and implementing complex systems. That's the way we think of the field that we're in. It combines all of these issues about dynamics and interconnection and communications, computing, computing and software, and one of the things that's changed over the last decade is there's a lot more interaction between computing and control than there was. These sort of had separated out. But I think that it really requires the combination of these views. You can't just look at it from the point of view of traditional controls. You can't just look at it from the point of computer science, but really combining these things together, and there's been a lot happening there. And some of the systems on the right are some of the more modern systems, so things like autonomous vehicles and rovers and other things. People are applying this in systems biology, and so this is a picture of the network that cancer governs cancer in certain situations. The internet is one of the world's largest control systems. Congestion control on the internet, how do you regulate the rate at which packets go out so that everything gets through when it's supposed to be. And the bottom is a battle space management picture. So I think there are a couple of principles that we think of as being broadly defining the field of control. One is that feedback can be used as a tool for managing uncertainty. And again, this is a broad statement. This can be applied to continuous dynamical systems like aircraft. This can be applied to the internet. This can be applied to chemical process control systems, to software systems. If you look at how you manage server farms, right, then you can use feedback as a tool for managing uncertainty in those situations. A second principle is that we can use feedback to design the dynamics of a system to do something we want. And so as an example of that, if you look at the system down on the lower left, this is a forward swept wing aircraft. And that system is unstable on its own. A pilot cannot actually control it. It departs too quickly. But if we use feedback, we can change the dynamics of that. We can design the dynamics so that a different set of dynamics. And a consequence of that is that we can use feedback systems to provide modularity, that is, to provide well-defined interfaces that allow us to connect different things to them and still have them behave as they're supposed to behave, because they are robust with respect to uncertainty, and we've designed the dynamics to be what they want them to be. So control theory is a pretty old field, but it's underseen huge changes in the last 10 or 15 years. And so if you ask, sort of what's new in control theory that I think people should know about in dealing with complex systems, there are a couple of things that I think are very important. So one is the role of online optimization-based control. That is, that computers are now powerful enough that the things that we used to have to do offline, we can now do online. And the picture here is a picture of a flight control system that we built at Caltech as part of the DARPA software-enabled control program about 15 years ago. And what we did in this system was that we computed out the trajectory for this nonlinear system with constraints and everything else for about the next 10 to 15 seconds. And we computed, here's what I would do if I want to satisfy some performance criterion for the next 10 to 15 seconds. Let me do that for about 100 milliseconds. And then let me recompute it and do it again. Right? And so I'm just constantly recomputing what's going on. So if the dynamics aren't quite what I think and I don't quite where I don't go for 10 seconds and figure that out. I go for 1/10 of a second, right? And then change what I'm going to do, right? Oh, I went a little bit higher than I thought, or I went a little bit faster than I thought, let me change that. And as long as my model's pretty close, right, the gradients are right, and you design it correctly, you can get that to work. And the place where things like control theory come in is if you do that wrong, you will sacrifice the long term for the short term. That is, in the short term, over those 10 seconds, you'll always do the optimal thing, right? But in the long term, you might go unstable or you might do something incorrect. And so control theory has provided tools for how do we put in the right short-term optimization so that we also manage the long-term behavior. So that's one example, and it's very much enabled by our ability to compute much faster. So when we did this, this was back in about 1999, we used a $20,000 DSpace system with a couple of custom DSPs on everything else. That amount of computation you now buy for $500 on a laptop, right? And so just what we can do in these systems is completely changing, right? And so that's had a big impact on the field. Another area is just the notion of using layering and architectures, and you already heard about this from other speakers. Just the notion that we want to think about applying feedback, not just at the lowest level of an architecture, right, the sort of real-time physical system, but at higher and higher levels of abstraction. So as we go up in a system, and the picture here is a picture of the power grid, we can think about the low-level control of generators and making sure that we're providing the power and as loads come on and off. But we can also think about higher levels of control. We might have a microgrid. We might do demand response at a higher level of abstraction. We can even go higher and think about market-based feedback mechanisms that we might use to regulate when you use power over time. You should use power maybe at night when it's not as heavily used so that we don't overpower the grid. And so those types of ideas are also feedback systems. And at every layer of these abstractions, we can use those feedback systems. Another thing that's happened is the role of formal methods, and Kathleen talked about some of this in terms of what can be done in terms of verification and model checking, and that's had a huge impact also on control theory. As we start thinking about how do we combine the continuous dynamics and the discrete dynamics, the continuous dynamics of the underlying physical system and the discrete dynamics from the computer-controlled part of all of this to do something better. And formal methods, properly adaptive, can do a lot. I'm showing here a picture of an electric power system from aircraft. This is a safety safety critical systems, so the specs on software for level A systems, so that is that systems that if they were to fail could result in loss of life, is no more than one failure in every 10 to the 9th flight hours. That's 100,000 years of continuous flying. I don't know about your code. I don't think I write quite that well. And so we maintain that, or we manage that by having lots of redundancy, by having very complex systems that have to shift over, right? If an engine fails, then you have to shift the power that engine was providing, right? If a contactor fails, you have to figure out how to deal with that, right? If a load shorts out, you have to disconnect it, all of those things, right? So we do that. You all probably flew here. Many of you flew here. You trusted, right, the engineers who designed these systems, and so they managed to do that well. It turns out that 10 to the 9th flight hours, about 30,000 flights a day in the United States. That works out to about 10 to the 8th flight hours per year, right? So on average, if you look now across the world, right, we ought to see a plane crash from a software failure every couple of years, right? That's about what it probably is, right? So we're actually at that. We'd like to be better. So how do we actually move past that? But these ideas of really relying on formal methods have played a big role in that class of systems. And finally, just the scalability problem that we see in so many technology areas. How do we move from control of the components to control of the systems to control of an entire enterprise, right? Where that enterprise might be a battle management system, as I've shown here, or it might be a supply chain management system, it might be the infrastructure that's going on within a city or within the United States or another country. And so I think those are areas where we're starting to see people scale up, we're starting to see people apply feedback in different ways. So I'll leave you just with a couple of ideas about how control theory might be able to help wrangle complexity. So one is this notion that we can manage uncertainty through the use of feedback. So here I'm showing an example of an electronic amplifier. And some of the components in an electronic amplifier are very precise, some of them are not precise at all, and we can use feedback to trade off so that we get precision even with robustness. And so, for example, a transistor might have a difference in gain of 50% or maybe even a factor of 2 from one batch to another, from one type of transistor to another, and yet we can get amplifiers that are extremely precise. We do that because you can get 1% precision resistors relatively cheaply. It'd be very hard to make 1% precision transistors, right? And so we use feedback to trade off by sensing what the actual output is and then using an ability to compute here in an analog fashion and apply an actuation, change the current going through the transistor. We can make sure that we maintain that output at the desired level. So that's an example of using feedback to manage the uncertainty. Here, uncertainty in components, but it could be uncertainty in the environment, it could be uncertainty in many other things. Another is the design of dynamics, and I gave you already the example of this forward swept wing aircraft, where we can really use feedback and our design of the feedback system to give the desired dynamics. Do you want this to fly like a 747 or do you want it to fly like an F-15? Right? We can design the feedback system to try and do that. There are physical limits, right? We may not be able to do one or the other or both, but we can actually talk about doing that in a way in which the feedback is part of the design parameter. And finally, sort of a corollary of these two things, the notion that we can use feedback to maintain modularity. Why? Because we can say, here's the properties I want of this particular subsystem, the input-output properties of that, and I want that to be true independent of what the outputs that I connect to it are and independent of what the inputs that drive it are, and I'm going to put internal feedback to make sure that that interface is maintained. And so by so doing, this becomes a component that I know that as I interconnect things on the backside and the front side, it'll behave as desired, and so that allows us to ignore what's going on the inside. Right? It allows a certain type of abstraction in which we can connect things. And I can do that abstraction in a kind of horizontal way between components at the same level or in a vertical way so that my lower level abstractions in some hierarchy maintain those interfaces independent of the commands, what's below and above, very much like the types of things that Kathleen showed. So those are, I think, some ideas about where control theory can help. It's not the only tool. There are many other tools, and you have to combine all of these tools. But I think there's some good ideas there that can help as we try and wrangle complexity.
Okay. So we've just heard from our 4 panelists 4 interesting approaches, different, some with some similarity, but different approaches to dealing with complexity. We heard from John, finding the right balance with standardization. We heard from Evan, recomposing systems, interfaces on demand. We heard from Kathleen, the computer science way, abstraction and composition, breaking it up in chunks. And we heard from Richard on control theory and feedback as a mechanism for handling uncertainty. I think some very interesting perspectives. But before we go to the Q&A, I'd like to do a poll of the audience to find out a couple of things. What is the level of experience with this topic? So if you've got a high level of experience, raise your hand. Okay, a medium and a low level. Okay, about the same as Breakout 1. Second question, which organization are you representing? Academia? Raise your hand. Government? And industry? Okay, so I think we've got a number more of industry in this session. The previous session, we had a larger number of government employees. So we should really get a mix-up of the questions this time around. Okay, so for Q&A, we've got 2 mics, one over here and one here. And if you've got a question for the panelists, please come forward, use the mic to ask your questions. So, is someone ready? Okay, well, let's go.
So my question's more geared to Evan. So as you probably know, been doing fusion for forever, and the problem that I have with the unified data models and other kinds of things you're trying to answer, but my concern is there's a lot of loss. It's lossy, right? So you're going to lose a lot of information. If every single system stored all of the raw data in some format that they wanted, then that whole path would work all the way through. Now, so I know you've thought about this. Also, in fusion systems or any other kinds of systems, you mentioned DSIGs up there, they're going to add to it. And they're not going to take the data just as it is and represent it some way or convert it as a process flow. Most of the time, the data is stored in some kind of data store. And there's not any uniformity with the data stores. So the interface concept doesn't work unless it's like simple process flow that's lossless, right? So how are we going to address those kind of things, specifically with the example? Because I'd love to get D6A and D6 Army and EyeSight and all these other kind of things to communicate together, and I'd love to use these layers of abstraction, but I see a few holes, so I'd leave it at that.
Yeah, so it's a great question. Just to repeat it, if all your transformations are ideal and perfect, then you don't have compounding errors that you have to deal with, and this concept works very, very simply. And of course, most transformations are slightly lossy to significantly lossy, and so the longer those transformation chains become, the more lossy you get, the more those errors can compound. And so we always have to worry about how many steps you've gone, how lossy is the transformations, and can you bound the lossiness or the distortion in each of those transformations. And so one of the things we do, Kathleen has mentioned the agree system from Rockwell. Rockwell has techniques where they can actually transform these graphs, these abstractions, into something that they can formally model, and then look at compounding errors and try and bound those through analysis mechanisms. So this gives us an ability to say, hey, we've got some confidence that this is something we can do, or it's uncertain whether we've met the bounds of acceptable error growth. Now, if you've not met the bounds of acceptable error growth because, let's say, your trains are too long, well, it's actually pretty simple. You just insert a link that connects the edges of those graphs to take far points on the graph and make them close points, and therefore, with a small amount of error, you can now expand your footprint of reachable states within your bounds. Your second question was associated with data storage and augmentation. I'm not sure I fully understand the issue there. The basic concept here is that I can have many different local data stores, and by automatically instantiating transformations between each of the different data stores, I can effectively federate or replicate the data through. Each store is still local. There is no concept of a common data store, and transformations are applied on the line. Now, this, of course, has the issue that you're applying many transformations. But for any particular instance, you know what transformations you need, so you can compile those down to optimized interfaces. These are great questions to explore, and I'm hoping other people will start to look at these sorts of questions also.
Okay, we've got a question over here.
Hi, I'm John Stevens with Cole Engineering. It seems that this is also for you, Evan. It seems to me there are a couple of assumptions that have to be true for this to work. One is that every piece of data you need in interface A is available in interface B when you're transforming that way. And the second one is, if you're making the assumption that you can go from node to node to node in one community because they're operating on the same standard, you're assuming that everybody in that community fully implemented that standard. And in my experience with simulation systems is that's almost never true.
Okay.
How do you address those?
Yeah, so there are two separate questions there, and I'll see if I can address each in turn. Regarding the first question, which was basically you need to have the source of the information be the superset of the destination of the information, and that's absolutely true. We're not talking about making up information. We're not talking about adding new information. We're not talking about augmenting the underlying data. We're talking about representations and managing the complexity of reasoning. It doesn't have to say that there's a one-to-one from the source to the destination, i.e. there's one path for all the subfields. It may be that each of the subfields takes different paths through the graph to recompose. But fundamentally, that information has to be there. And now I've lost the second question. It was on standard implementation, right? There is no standard here. No one is implementing a standard, and they're implementing a portion of the standard or their own local version of the standard. All that's necessary is that there's pairwise interactions describing the relationship between those implementations, and then you can effectively dynamically re-implement whatever standard is needed at that moment, if that makes sense.
Well, close, but it sounded to me like if I have a community of systems over here, 5 systems that implemented some standards so they can talk to each other, and I make that connection from that standard to whatever the interface is on the other side, any of those 5 should now be able to talk, but that assumes that they all fully implemented their own internal standard before you ever got there with this technique, and I know that's often not true in the systems I deal with.
Yeah, absolutely not true, and it's not an assumption at all, in fact. So the 5 subsystems can each implement their own standard and have a linear chain through them, and you get full interoperability, having no standard in community A. And similarly, you could have 10 systems that each have their own standard with a linear chain in B, and by connecting those two, you can now have 15 different standards and still full interoperability. And I'd be happy to go through the details offline if that's of interest.
I think so. We've got another question over here.
I'm really sorry, but it's one more question to you, Evan. But maybe I'll phrase it in a way maybe that you guys can all speak to it. The question is, sometimes you have data that when transformed, for example, becomes less meaningful. So let's just say a circle has a center point and a radius, but if you transform it, you change it, suddenly it's the vertices that define kind of an approximate circle. So how do you preserve meaning when going between different interfaces? And so maybe this is something that the first speaker can also speak to.
Do you want me to take it?
Yeah,
okay. So you're absolutely right. If you'll have different fidelities of representations, and some bases will represent information more efficiently and accurately than other bases, and there's no guarantee that the path through the graph will retain the precision all the way. Now there may be the reality of what will often happen is there will be multiple paths through the graph, some of which may retain more precision but at the cost of more computational cost to do the full precision transformations, where other paths may be approximate transformations that give you the flavor, but with a compounding error, but much, much more computationally efficient. And so you need to be able to designate both the accuracy and the computational cost, and then at design time use those design space exploration tools to balance, as John talked about and others have talked about, whether you need the computational efficiency of a less accurate or the precision, but willing to tolerate the slower.
Okay, Kathleen, did you want to add something to that?
No, that sounded like a perfect answer.
Okay, so we're back over here.
Yeah, sorry, Ivan, my question is not for you.
Makes me happy.
He didn't get to talk very much in the last panel, so this is good.
Sandeep Nima from Vanderbilt University. I guess my question is both for Kathleen and Richard. You guys both talked about formal methods and sort of application model checking techniques in the different problem domains, right? So one thing I guess, it's probably you've seen pretty much, right, that the scalability is a big issue, right? Especially for cyber-physical systems, high dimensionality becomes a problem, right? Any current techniques, they just don't scale at that level. Now you see the systems sort of getting more complex, right? So how do you reconcile these two together? Do you see some breakthroughs coming in your areas of research that will help the verification problem for large complex systems?
I can go if you want. All right, so I mean, a couple of things, and Kathleen's more the expert here than I am, but just in our application. So one is that just the the size of systems that can be handled these days really is getting very large, right? And so we're getting up to 10 to the 11th states that people can do model checking on and other things because the algorithms are getting much better. So first off, computer science tools are really catching up and getting to very complex systems, and so that means that Things that you would never think about applying them to before, you can apply them to now. Not everything, right? So Kathleen talked about, for example, the microkernel and other things. The others, you have to decompose it, right? You have to break these down into smaller pieces. You have to use, for example, maybe an assume guarantee framework to allow you to decompose it and then recompose them back together. And that's what we've done, right? So you might say, okay, I'm going to reason only at a certain layer of abstraction. I'm going to break that layer of abstraction up into different components. And I'm going to maybe by hand construct, right, my interface contracts that are going to allow me to reason about a relatively small piece of the system and show that it satisfies those interface guarantees under certain assumptions. And then on this side, I'll show that given the things that were guarantees here, those will be assumptions on the other, right, and connect them back. So I think assume guarantee frameworks, decomposing those is still a challenge, right? So how do you come up with that? That's still manual, but I think that's the next thing. People are starting to say, how do I synthesize the contracts, right? So you give me a doors database of things. How do I break that down into a bunch of, sub-components, right, with formal guarantees on each one? Those are the approaches. They don't solve every problem. Doesn't mean we shouldn't be looking at where we can use them.
And then there's a lot of research going on right now in the computer science community on model checking and how to scale it to larger systems. So there's a lot of work on how you represent the collection of models, right? In terms of like the beginning model checking was where you only had a finite collection of models and you could search the entire space exhaustively and there were clever representations to do that. But when you went to software model checking, the state space became infinite, so you couldn't do that. So you had to come up with clever ways of representing the state space implicitly instead of explicitly. So there's a lot of work on improving representations. Another thing that researchers have started to do is small models. So instead of searching the entire space, you have some kind of step index function and you only search for K up to some level and you kind of push K as high up as you can and you figure, well, I've explored this much of the space and I can't do the rest of it. But maybe you have some other kind of argument that says why the K that you were able to get to was sufficient. So this is an ongoing and interesting area of research and hopefully the answer 10 years from now will be better than it is now.
Thank you.
Sure.
Okay, let's come over here.
Yeah, I'm Jeff Bowling from Carnegie Mellon. Sorry, this is for Evan again. I'm just a natural skeptic. You talk about automatically composing new interfaces. So, and you've said no standards, but it seems that at a minimum we have to agree upon how we describe the interfaces then at that point. I mean, it's another level of abstraction, obviously, that we've agreed upon a common way to describe our interfaces, but is that, can you tell me how you do that?
Yeah, it's turtles all the way down arguments. It can be hard to not have any global standard anywhere, and we've worked very, very hard to try and find ways to allow for heterogeneous descriptions of the transforms that each then compile down. Obviously, when you build an interface, it's going down to machine code, and that machine code can live in different hardware architectures, so you've got heterogeneity there. It can live in different intermediate low-level languages like Java or C++. It can live in different domain-specific languages to express the original specification. And that heterogeneity is possible and allowed with some use of abstraction and composition at a few key points to basically allow different methods to synchronize. And there's a couple of different ways you can do that, and I'd be happy to talk through the details of using either on-the-wire formats or in-memory formats or language-level formats or DSL-level formats. And by putting a lot of different places to synchronize, it's often the case that you can find at least one synchronization point, allowing a massive amount of heterogeneity while still achieving interoperability.
Okay, I think there's a question here.
Yes, I'm Dr. Amy Magnus from the Air Force's grad school. This is a question for Professor Tufts. I mean, for Kathleen, I'm sorry.
For me?
Professor Tufts.
So one of the things that the engineering physics department is, what we like to do is develop sensor concepts and the physics-based codes that are associated with them. Now, there is a generation, we develop these codes over time, and we think that the development process is interesting because you are going towards a customer in a particular application, but when you're generally looking at the phenomenology and the data that you can get on that phenomenology, you create general models that you refine over time. So the idea is that these codes that we generate are actually referential documents that have a history associated with them too. And capturing that may make these problems with making things more explicit in the final project in the final product that you produce is that there's stuff that we're kind of like leaving on the table and not handing over to people. And so one of the things that I'm looking for is tools that would help us, you know, as we develop code, is to extract those things that might be interesting towards, in other words, to hand off. And do we know any tools that are looking at how, you know, looking at code as referential documents that have a historical basis and also a basis where the algorithms mean something. The algorithms have a history themselves that are associated with papers, phenomenology, and you know, just computational power in many respects.
Right, so that's a lot of questions tied up in one. So let me address some of them. So, you know, code as documentation is a really powerful idea. When you work in domain-specific languages, you can raise that level of documentation even higher so that the code that you're writing ends up looking like your understanding of the equations and physics that you're trying to model. So that's an ongoing trend in the sort of programming language community, is to make it easier and easier to build kind of domain-specific high-level languages where you can just read off from the code the understanding of the domain that you're working on.
Yeah, and specifically, if it's somebody's work that you could point to and say, you know, that type of work might be very effective.
Right, so then when you're talking about, okay, here are the equations, and you have a DSL that compile those equations down to actual executable code, but now you're saying, well, but I want to be able to reference where those equations came from, right? So that is a branch of programming, software engineering called literate programming, where you annotate the code with metadata like that, with references to papers. There are some systems that have been developed to do that. I'm not sure that there are sort of a market dominant one, but if you people start to embed that kind of information in their programs so that it can be extracted in a documentation tool. Howie Schroeb, who's at MIT right now, has been working on a system to help capture those kinds of design documents so that you leave a legacy of the entire development process behind, so that if people come downstream who weren't connected, they can go through all of those notes and extract kind of the implicit assumptions. So I would encourage you to look at his work if you're interested in more detail there. Howard Schroeb, he's a professor at MIT.
Okay, I think we'll move over here. There's a question.
Sure. Drew McKechnie, KPMG. While many of my auditor colleagues are very familiar with a specific brand of financial standards or control theory related to risk and that type of thing, I'm sort of more of an inch deep, mile wide strategy consultant type. And so I'm trying to look across a lot of the things you said. There's a lot of complementary aspects and there's some aspects that are in conflict. Can anybody speak to, you know, rather than treating this as a buffet, are there frameworks, are there ideas, are there approaches that leverage this multidisciplinary approach better than others? Because I think each discipline has a lot to offer, but are there people that have applied these things in concert effectively? Thanks.
Richard?
Okay. So, yeah, I think that the notion of putting all of these things together gets complicated. I think the best that I can say, and maybe others have other things to say, is that, you know, certainly one thing that helps a huge amount is to try and get more model-based about things, so that you're describing your understanding in these different domains. And then we can start working on, okay, now how do I combine models from different domains together so they can reason about what's going on in some way. And so that's model-based is a system. I mean, you can apply that to anything, right? And then you can talk about what are the models in different domains and how do I apply those. So that's certainly one thing that I think cuts across all this. And we see a lot of things going on in model-based development. I think some good, some bad, right? And another I'll say is, and it's related to this, is the notion that if we have a model of what something is, we have a specification of what something is, sometimes we can synthesize what the answer is. And again, that cuts across all of these levels, right? We synthesize control systems. We don't manually design control systems and then go back and verify them. That's what we did a long time ago, right? When we do something like an optimization-based control system, we say, here's a description of the system, here's a description of the specification I want to optimize some cost function or something like that. And then we just solve that. We synthesize that problem. And again, I think that's something that cuts across all of these domains. And so, you know, the notion of model-based development as an approach to connecting these things together, the notion that if I am doing model-based development, sometimes I can start doing synthesis and optimization and other things. Code generation, automatic code generation is a form of kind of model-based synthesis. So.
Anyone else would like to add anything?
Yeah, so
John?
Without getting into specifics of detailed implementation stuff that we've done, I'll say that
employing these principles at multiple levels is, in practice, is going on. I mean, the employment of an open architecture standard and then looking at ways in which you can employ adaptation at the edge such that you can start to embrace a lot of the stuff that Evan's talking about without it being a, dive into the deep end of the pool. Certainly having the feedback mechanisms in your system such that as your system makes decisions and starts to move down a path, that you get a feedback loop that comes back in and specifies that, maybe that wasn't the best thing to do, or you've now got bad information and you need to respond accordingly. There's absolutely cases like that being developed today that are reasonably advanced. It's just a matter of, as I said in my talk, it's finding the balance of these different technologies and applying them in the right way. And as the research that our academic team continues to forge down, that it's going to give us the opportunity to better embrace these tools at an even deeper level than we can do today.
Okay, we've got one more question over here.
Hi, Alan Wood from Oracle. This is for the entire panel for a change. So my idea of a complex system is one that's continually evolving. In other words, while you're designing, while you're building, while you're deploying it, everything changes about you. The customers change, the requirements change, the mission changes, everything changes. Plus, you're stuck with often legacy code, legacy components, and so forth. So my question is, how do your approaches deal with continual change and using components that don't conform to the things you'd like them to conform to?
Sure. So, yeah, I'll kick it off and then we can go down. So I think that the basic premise there and how the strategy to address that challenge is centered around the modularity facet that was discussed. You build your components, and those components unto themselves can stand alone and don't really form a system unto themselves. And so you build those modular components, expose them with the right pieces of information, or how they're invoked externally and what type of information they publish when they're invoked. You put those building blocks in place, and then systematically you can go through and start to compose your system. If your requirements do happen to change, at that point you're only messing with one of the components in the architecture to facilitate that change, as opposed to having to promulgate that change throughout the entire system that you developed. And so I think the modularity facet with that composability element that was bridged in my discussion and Evan's discussion is really how that gets addressed.
Yeah, to expand on that a little bit, we've long thought about complexity in terms of space or detail, but less so in terms of time, as you've described it. And again, abstraction and composition are going to be the way that you handle complexity in any situation, but we'll shift from one where there's sort of a static abstraction, a simple abstraction that's known for all time, to one where it's an adaptive abstraction, either through mechanisms like I described or mechanisms like Richard described of feedback control, optimized online control, where you're continually changing the abstraction to still give you the confidence that you can count on that interface without knowing the details behind it, but that interface is continually changing to keep up with the environmental shifts or customer requirement shifts that you're seeing. And the community for the first time is sort of bridging these different areas into one more unified theory, I think.
I would add to that, I think that domain-specific languages and model-based development are important components to that, where you can capture and relatively easily change the high-level things that have changed in the DSL level or the model level, and then generate the low-level code that's very platform-specific. So instead of replicating the effort at the writing a huge amount of code every time, you just make relatively small changes at the high level of the system and then generate the low-level code automatically.
Maybe just the last thing I'll add, and maybe harken back to those of you who were there to the talk that Alberto Sangiovanni gave. Right? I mean, you have to think about the architecture, you have to think about things like platform-based design, you have to think about the fact that I know my components underneath are changing, and so what's the layer of abstraction at which I can ignore that? And the internet's the obvious example in which we've sort of gotten that right, but it's maybe important to point out that, the current TCP/IP protocols weren't the only protocols that were out there, right? There were half a dozen different ways that people were trying to do networking. It was the one that worked, right? Because it allowed that evolution over time, right? So one of the other things is, unfortunately, we probably have to try multiple things and see which one works, right? It's a lossy mechanism, but I think that's what, nature and engineering teach us, right? Is that, it's hard to guess ahead of time which one's going to be the one that can evolve and live for 30 or 40 years.
Okay, are there any other questions? Okay, let's give the panel a big hand for doing a fabulous job. And thank you all for coming. That wraps up the session.
Thank you.